So I'm representing SimWave. I'm the chief scientist and a co-founder of SimWave, and Abdul is the CEO, and he's gonna do the second part of the presentation. So you can sit down. Yeah. So okay. So we are Canadian company. So we are not far away from here. We're located in Waterloo. It's just 1.5 hour drive to here. And what we do is we are quality of experience company. So basically what we are trying to do is to provide industry with the tools to monitor and measure quality of experience. And also, on top of that, once you know the quality of experience of your video content, you want to optimize your user experience and also try to cut bandwidth cost, because you have more knowledge about the quality of the video. You know how to compress the video. Okay, so talking about the video, first I want to show you a piece of video. Actually, that's the video. Right? So probably this is going to be the most hated video in this world, right? So people don't like this, right? So stalling is really a big problem in today's video streaming video communications. People don't like this. Of course, this is going to affect your quality of experience. The second type of things that will affect your experience is something like this. Actually, this is a real screenshot from 2014, the streaming video of 2014 World Cup. If you see something like this, you don't even see who is playing, and you don't see where is the ball or something. You can still see something, but the thing is, if Coca-Cola is putting money in this, you're streaming this, Coca-Cola is putting money in this, they're not going to be happy about this, because people don't want to watch a video like this. And it turns out when we watch this video, our experience that the quality is actually going up and down. This is, of course, one of the low points of the whole streaming process. But the thing is, people will remember this, and people will say, okay, this is a crappy streaming experience. I don't like this. And people will go away, and Coca-Cola is also going to go away from you. Right. Okay, so actually there are some scientific studies, there are reports and surveys about how people care about video quality. And basically, based on some recent surveys, 66% of the viewers will abandon a video when the video quality is poor. Right? Also, 39% of consumers are planning to switch to another broadband provider in the next 12 months. If the video quality is poor. So this is something really important. And viewers viewing better video picture quality will watch 25% longer time. This will also give you more chance to monetize your video streaming. And this is some detailed statistics about people's views about quality. Among all the factors that could affect people's quality of experience, you can see actually the playback quality is of poor quality is the most important because you have 66%, about 66% of the chance that people will stop, abandon the video they are watching. Okay, so of course the industry cares about quality of experience. Everybody knows it's very important to have very good quality of experience. And actually, the industry care about this, and they even give an Emmy Award on this topic. So in October 2015, which is just a few months back, and the Television Academy is giving an Emmy Award to the invention of the Structure Similarity Index. For some of you, you may not have known this. SSIM is the one that is winning one of last year's Emmy Award. So people really care about this. So I'm very happy, I'm very honored to be the creator of SSIM and receiving these Emmy Awards. So the question here is are we going to be happy about SSIM or not? Of course, myself, I got the award, I'll be happy, but how about the others? How about the the people who really want to have something to use to monitor, to measure video quality experience, are they going to be happy about SSIM or not? I think if people ever is happy about that, then it has to be even 100 times more popular than what it is today. So in other words, there are some limitations, some problems with SSIM. Even though it's a winner of Emmy Award, a lot of people are using that, still people are not happy enough. So the next couple of slides, I'm trying to explain why people are not happy. So there are actually a lot of real-world challenges that stop people using SSIM in every day, in every places. Right? So what are these challenges? So basically, you have some desirable features when you have a quality of experience measurement. The first obvious thing is it has to be accurate. So it has to predict how humans perceive image and video quality. And in that sense, SSIM and some derivative after that, such as the multi-scale SSIM, is actually doing an okay job, not a great job. It's doing some job. Okay, so the second one is, of course, you always want to improve the accuracy further. The second thing is you want to have something fast, right? So you are delivering video. You cannot wait. So the video is coming in and going out. You have to do these things in real time, and hopefully even faster than real time. You should be able to know the video quality. So speed actually is a very, very important factor. Okay, so but on top of that, there are something even more. For SSIM, you can further refine that, increase its accuracy and increase its speed, but there are some other limitations. SSIM cannot even be used. So for example, device adaptation is one important factor. So for example, you have the same video, right? So compressed video. You're watching the video on a cell phone or on a big TV. You're going to get a different experience, right? So if you have a big TV, you watch extremely very close to the TV, you're going to see a lot of artifacts. But on a cell phone, maybe it just looks okay. It's like a pretty good quality, right? So in other words, the visual experience will be different depending on the device. But all these existing quality assessment methods, including SSIM and other things, most of them are giving you just one score, just about this video content. Right, so you really want to have some tool that can give you a prediction based on the device. Okay, so another thing is these days, these people have this hype of high dynamic range, and this is something that a lot of people is going to predict. This is going to be the next future, next thing that's going to be widely deployed in the real world. So, but how we're going to measure the quality of high dynamic range image and video? This is another thing that the old method won't work very well. And another thing is the high dynamic range HDR content might come earlier, but most of the consumers don't have a HDR TV or monitor, things like that, to watch all this content at home. Right? So a lot of people are still going to use the standard dynamic range device to watch all this content. And to do that, you have to do some tone mapping. You have to convert high dynamic range to standard dynamic range before you can show all these things. Right, so then there's a problem. So suppose that the source, the master file, is HDR content, and the content actually is showing on the consumer device is LDR content. There's some conversion between them. You can't even compare these two videos, right? So because each pixel is not even on the same dynamic range, how are you going to compare them? So the current quality assessment method is not going to work in this case. So you really want something that works for HDR high dynamic range and also cross dynamic range quality assessment. So another thing is cross resolution. So this is also a very practical common issue, right? So we got this master file, it's probably 4K UHD or very high definition, high frame rate, and you want to create derivatives, right? So because the delivery this issue of the consumer is going to have a different device to watch the video, you have to convert this into 1080p, 720p, 480, 360, 144, like YouTube, the lowest resolution is going to be 144. So you have to do this conversion. Okay, after you do the conversion, how are you going to evaluate the quality of this, the video you are actually delivering using the reference which has extremely high resolution, both spatial resolution and temporal resolution could be 60 frames per second. All these converted only have 30 frames per second. How are you going to compare these two content? Right? You can't even have this correspondence and do the comparison using the standard approach like PSNR or SSIM. Right? So these are the really the challenges. It's stopping you from using all this because all these old methods won't be even applicable in these cases. Another thing is cross-content. You know, say if I use the same bandwidth or say the same QP value, if you are familiar with video compression, to compress different content, you can compress something like news, very simple content, or sports, people are moving really fast, or some video with a lot of texture, and so on. The complexity is going to be different. Also, you can have sports video, cartoon video, all these different types of content. If you use the same parameters to compress all these things, then the quality is also going to be very different. So you really want to have a tool that gives you a common, like normalized evaluation, so that the quality of 90 of a sports content and the quality of 90 of news content, these two values are comparable. They have meaningful numbers created out of these quality of experience measurement tools. So these are the things we really desire to have, but it's really hard to do with old stuff. Okay, so there are also a lot of desirable things, especially for those engineers who are working on video compression or creating this content. You really want to sometimes have the detailed quality map. Of course, Abdul is later going to show you this quality map. I'm going to show one quality map later. It means that you really want to predict the quality of the image and video at each spatial location, at each time instance. Right, so that you can, if you have a video that has a little bit quality problem, you can locate at which time instance and which frame, and inside that frame at which location you lose some details, you lose the quality. So you really want to have some tool to tell you something like that. So this is another desirable feature to have. Okay, so just now I talked about structure similarity, SSIM. Even though it's winning the Emmy Award, it has all these troubles. It doesn't solve all the problems. It doesn't have the desirable properties I talk about. So because of that, we are trying to develop something even better. So something what we call Simplice. Of course, SSIM is something that we published more than 10 years ago. So as a university professor, we have a research lab with a lot of active members. Even now we have like 3-4 postdocs and 5 PhD students and a few master's students to work on different aspects of image and video quality assessment. So we did a lot of research in the past 10 years. We didn't stop after we published the SSIM paper. So what we can say is that after 10 years of research, we have done a lot of new things. So we have major breakthroughs, including all these features I talked about just now. So now we have a new measure called Simplice. Simplice is you have the highest accuracy, so it's a big improvement on top of even SSIM, and also it's getting even faster than SSIM. It's you can using Simplice, you can even implement that with real-time software solution. Abdul is going to demo that. So he's going to run this Simplice on this laptop in real time. So it's completely software solution real time. And also Simplice is giving you intuitive and uniform scoring across content, just like what I said. If you got a score of 70, it means 70. So 70 means that the total, the whole scale is going to be between 0 and 100. 70 is at a good quality range. It's not excellent quality, but it's in the good quality range. But for different content, 70 has the same meaning, right? So it's a good quality content. And also, Simplice is able to do cross-resolution assessment, and it also gives you different prediction depending on what device you are talking about. Right? So it gives you this device adaptation. And also, it computes cross-frame rate assessment, and it also has have the capability to deal with high dynamic range image and video. Right? So hopefully, we're going to have a little bit more demonstration time for demonstration. But for now, let's first look at the accuracy. So PSNR is the Simplice, and previously most people are using PSNR to evaluate image and video quality. And here we did some subjective experiment. Here I'm plotting two scatter plots. In each of the scatter plots, at each dot there is going to be one video. And the horizontal axis is going to be the objective quality measure to measure the quality of that particular video. And the vertical axis is the mean opinion score of the human subjects. So in our lab, we are constantly doing a lot of subjective testing in our lab. So we ask people to evaluate video quality, and then after you have many people evaluate the same video, then you can compute mean opinion score. This is something, the mean opinion score is the thing that I'm plotting on the vertical axis. So each point is a video, and I'm using the horizontal, which is a prediction of the quality, and the vertical is true quality by humans. And you really want this scatter plot to be very narrow, right? So that once you know the objective measure, you can use that to exactly predict how humans think about the quality. So you want this scatter to be as tight as possible. Hopefully just align this diagonal line. That would be the perfect case. Okay, you can see that the PSNR is not really doing a great job. And Simplice is the thing that I have been talking about just now, is doing a much better job. You can also do this comparison with SSIM. SSIM is right, so is again very, very well known. And if you look at the performance, still you're going to have some trouble. Simplice is doing a much better job. Okay, so just give you a little bit of favor because at the end of the list I gave you before, I talk about we can do work with high dynamic range image. Of course, this is the place we cannot show we don't have the display, the monitor to show high dynamic range image. Here I'm showing like a tone mapping result. So this is one of the results, some of the things I'm talking about. Okay, suppose I have a high dynamic range image, right? I want to show on a standard display, like what I'm using here, like here. What I need to do is to do this tone mapping. I convert 10 bits, 12 bits into 8 bits before I can show on this. But then you have different tone mapping algorithms. So these actually are the outcome of two tone mapping algorithms, both from Photoshop. So it's not some magic thing. It's just in Photoshop you can have options to do this tone mapping. But if you look at these two images, right, so overall you say, okay, the brightness, I like the bottom one. It looks brighter. But on the other hand, if you look at the window right here, the top window right here, is all white. The details are gone. Why you know the details are gone? You look at the top. Because in the other image, you know there are details in the window. So in other words, the top image, you don't like it because it's too dark. And also in the black region, you lose the details. But on the other hand, the bottom one, actually, you don't like that because in here, you lose details in the very bright region. So we cannot say that there's a perfect tone mapping in here. Both of them has their problem. Okay, so this is what we observe. How about the algorithm? The algorithm is giving you detailed quality map. That's something that I just mentioned earlier. So it's giving you, so if you look at the second column, this will be the finding scale quality map of these two images. So for example, the bottom one, you know, I lose a lot of details in the very bright window, right? You see a dark disk in the second picture there. So this quality map is giving you a detailed prediction at each location in this image, darker means lower quality. Right? So it's giving you a map that tells you exactly where are the problems of this particular picture. Right? So that's what we call quality map. So this is how Simplice and this, our new algorithms are working on HDR images. Okay, so I think I'm going to hand over to Abdul. He's going to talk more about how we're going to use these quality measure in real system, how we're going to use this in the real world, and also show some demos.
Thank you, Professor Wang. So let's look at the software first and run this. We talked about a lot of theoretical things, and so we want to see how does practically it looks like if we want to have a quality of experience measure running, what kind of numbers do we get, and what's the result at the end of the day. So here we pick a test video. Of course, we have the pristine quality video and number of frames that we want to process. And if you continue, then what you get in this software here is a test video where you have blockiness. Some of it is visible, although the room is not totally dark, but you see some of the blockiness in here. As Dr. Wang showed before, we have a quality map on the right side. Again, dark means lower quality, bright means better quality. So when you play the video, the map is being computed in real time. There are some scores that are being computed. I'll get to those as well. But various artifacts that you can have here in terms of blockiness, loss of details, blur, they are highlighted here. So let's go to the bottom right corner. So you have the Simplice family of algorithms that can provide all of these properties. Here you have device adaptive scores. So just imagine this is a 480p video. If you are watching this on this big screen, then the qualities, of course, would be really poor. But if you're watching on a small screen like an iPhone, really low resolution, then the impact of scaling and all of these other impacts due to viewing conditions would not be that obvious. So you have the highest score on an iPhone, let's say 5S in this case, and the lowest score on a TV in an expert mode. So since we can adapt based on viewing conditions as well, the Simplice algorithm can do that, considering viewing conditions, including device properties as well, and the scaling impact. So you get the overall prediction. But again, the scale is from 0 to 100, divided into 5 different categories, and the scores are being computed in real time. So the reference video that you have, of course, the full reference measure that you have on the right side does not have to be same resolution, frame rate, or dynamic range for that purpose. So at the end, what you get is at this point, we can predict various behaviors of the human visual system to get to this point where we can do it in real time. So it's about the state-of-the-art technology where we can really understand how humans perceive quality and implement it in software to achieve this kind of performance. So getting back to that, how this would be used. So first and foremost, the most easiest way of doing that is you just want to monitor content, right? So you have a very simplistic workflow. You have the content being produced here and then encoded once or multiple times. Derivatives are being created through content delivery network delivered to different devices. So you want to understand what the content quality is like from the experience perspective as it's being delivered. So that's the straightforward application of this. And this allows you to not only monitor quality, but also control quality. Because now I'm going to talk about the different mindset when you deliver video. It's not just based on selecting bit rates anymore or selecting a table based on configurations of encoders. Sure, you have practical constraints, but you want to talk about what people care about. The common viewer cares about the experience they are getting. So you want to use a language to define that and use that as a driving factor to deliver video, to really revolutionize how we perceive quality. So it allows you to control quality. That's where we want to get to at the point. And not only, so you can always get higher quality by spending more bandwidth. So there is no, that's not a secret. But at the end of the day, you want to use the existing networks to be able to deliver higher quality. So you want to see how to optimally use the bandwidth that you already have available to achieve the target quality at the optimal bandwidth. So that's where it gets really interesting, because you want to use the QoE measure not only to tell it, for it to tell you that something bad happened. You want it to take control of the video delivery process and have it that's the real advantage of getting this accuracy, that you want to give it control to take decisions on your behalf for you to make sure you can get that target quality. So it's ideal for bandwidth cost reduction, and of course that would help reduce churn. So let's talk about some practical ways of how, or some examples of how this can optimize video. So I have a few clips, or specifically images in this case, from Tears of Steel. It's a very common movie that we use these days to compare algorithms or various systems as well. So we are looking at three things here. First of all, the content quality that you perceive here, first of all. The second thing is you want to look at the bit rate that you're spending on this scene to encode at a quality that's defined based on Simplice. So here, obviously, the quality is not that good. The Simplice number is pretty low. Bit rate, you're not spending that high. So you start improving bit rate that you spend, and at the end, the picture quality gets better and better. Your Simplice score gets better and better as well. More crispier, more detail, less blockiness, less loss of details. So 2 megabits per second, you have 55. 3.3 megabits per second, you have 67. For example, if your target quality is edge of excellent, then 80 is when you get at 9 megabits per second, you get excellent quality. Now let's look at another scene very close by. And let's say if you're encoding, typically like how video is delivered right now, if you were to achieve your target quality based on that scene, you would say, okay, let's use 9 megabits per second. So let's look at this scene, what happens with this scene if you encode at different bit rates. So at 448 kilobits per second, you are already at 56. 67 at 600K, 1.277 at 2 megabits per second, you get 80. So here, based on your target quality, you want to adapt how you want to use your resources to get your target quality. And that would give you not only your target quality, first of all, because that can directly drive business models, but also it can allow you to use the optimal bandwidth that is required to achieve that quality levels. So this is a brief summary of that. So you have how the video is being streamed these days. You have different derivatives at different bit rates. And at the end, you want a QoE-driven streaming and not the best effort scenario where whatever bit rate you can do, you would just do that irrespective of whatever quality gains it can give you. So at the end, based on different segments that you're streaming, you want to switch to that target quality segment instead of doing 1 megabit per second if you can just do that. So the second, that's the overall idea. There are two ways of doing that. So first way is to use the quality experience measure as a feedback to produce better encodes. So instead of doing constant bitrate encoding, you want to do constant quality encoding at the end. So you want to tell your encoder that let's encode at 80 and give me the minimum possible bitrate that's possible. So that's one way of doing that. So ideally, by doing this, you can save 50% in bandwidth savings compared to conventional systems. And that's basically one of the biggest problems with existing standards as well. None of these, everyone knows PSNR does not work well, but still we are using PSNR. We are actually using PSNR to develop encoding standards as well. This is a dimension that can give you free gain. And let's use that and to for these benefits. The second way of optimizing this is use the quality of experience measure together. So whatever content you wanted to produce, you produce that content. Now you want to measure the quality of that content. So you use whatever quality experience measure, in this case Simplice index, to compute those scores, and then do the switching between different segments that I just showed based on quality experience index to achieve that target quality, and then achieve also at the same time the bandwidth savings that can easily be up to 50% on average. Because you have different dimensions for optimization. You have the device dimension, right? So you are giving the target quality, achieving target quality for that specific device. You have the resolution dimension. So you want to make sure you use the optimal resolution for that device. So that gives you additional gain. You achieve bandwidth savings based on the variation of content. So you give exactly those many bits to that specific part of the content to achieve those savings. So basically what it does is it allows you to control quality per view. That's the highest level of granularity that you can get. So you can tell that in real time that I'm delivering this video file live on demand to this specific user, and I want that guy to get this target quality, of course, based on the constraints. But that's the level of granularity that you can get to. So that's the overall message that we want to give here. Let's move away from bitrate-based mentality, and let's move towards quality of experience-based mentality, because that's what the viewer is experiencing. Viewer does not know about bitrate. And as a result, there is a lot of gains, including achieving your target quality and saving significant bandwidth. Thank you.
This is a really interesting idea. Have you been able to, I guess, apply this practically to any of the encoder manufacturers who are working in the adaptive bitrate encoding?
So let me show you, actually, since we had 40 minutes, so in the spirit of time, I did not show the demo. That was originally part of the plan. But here you have an ABR stream. That's the way you deliver. So I took, again, the stream Tears of Steel, and you have, let me go to some interesting part. You have optimized video on the right side. Both videos have the same target quality, but the size of the video on the right side is 53% smaller than the video on the left side. So they are not perfectly synchronized, as you can see in this case. But what the bigger message that I want to give is right here in the center, is you pick the target quality that you want to deliver. And at that specific target quality, if you want to deliver 80, then at that specific target quality, your bandwidth is optimized. So in this case, for target quality 80, there's savings for 47% savings. So we have done a lot of integrations with existing encoders, like X264, X265, and other encoders as well. So it's typically easier to work with software encoders because you easily get API calls to control the behavior of the encoders or drive those encoders. We are also working with our current customers to all integrate with existing commercial encoders so they can provide us APIs and we can control their behavior as well.
So the actual codec, software codec writers as opposed to off-the-shelf encoder platforms or consumer.
Yeah, if you already have a preferred encoder, then that can be optimized. Or if you just open to any encoder, then we can recommend some encoder as well. That would work best. But this is where you have to re-encode, similar to how Netflix said per title optimization. They are picking a specific bitrate on the whole file level. But here you're adapting based on not only per individual segment, whatever that segment you want to consider, you're adapting based on device, you're adapting considering resolution, frame, all kinds of aspects when it comes to video. So the other way is through smart streaming if you already have the content encoded.
Are you finding that, I'm assuming you've checked a great number of codecs, that certain codecs have a sweet spot in terms of a specific, we'll say, average bit rate given a quality value, or is it sort of more of a random thing?
So comparing encoders, this is a tool that we are providing you to make that decision, right? So we are giving quality index for you to do that. But one of the biggest problems that people want to solve using a quality of experience measure is to determine the optimal table of bit rates that they would use to deliver content. So this allows you to set quality levels and then set target bit rates if you have to do that. But if you are using 8.5 megabits per second as your highest profile, that may crash the internet, break the internet. If you are using 4.5, that may not, but at the end the overall quality would be low. So we are giving you a tool to get to that, for that specific encoder, get to that target quality level that would be optimal. Because we also take into account buffering events on the player side and variation in quality and all of that. But typically these days there's a lot of discussion. I work with various technical groups as well, where someone is saying we want to use 4 megabits per second for 1080p. Other guys are using, let's use 3 megabits per second. it's useless conversation, because it really depends on the content, really depends on the encoder type, it really depends on so many other factors. So you cannot be foolproof. And at the end, even if you pick a really high bit rate, then how would you deliver that? You have to really have high cost for that. So it's a very difficult question. I tried to cover different aspects of that.
So, if I understand then, can your software take an incoming stream, an uncompressed stream, analyze that stream, and then give a prediction of the right coding rate, segment by segment, and then use that information about the correct coding rate to feed into an encoder, which can then comply and code it that way?
Yes, so that's the first way of doing optimization.
Okay, because the way you've been presented is as a measurement tool, it appears to be I have the source, I have the output, and now I'm comparing them, and I can tell you what the quality is of the encoding. I guess the money is when you can predict the encoding level bitrate requirement, and then make the encoder do the job, right?
Yeah, so as you know that there are various ways of doing encoding. It makes our job easier if it's 2-pass. Otherwise, in a single pass, we have to predict the quality based on the behavior of the encoder that we have to predict as well. It's easier if you already have 1 pass available, so in the second pass we can make sure that we achieve the target quality and the bandwidth savings. So first pass is where we have to predict. The second pass, if there's something that we can do, then that's relatively easier for us to do. But the other way is, if you already have your assets encoded, then for over-the-top delivery, you can pick your optimal bit rate for that target quality. Then you don't have to really worry about encoding at all.
One more question. You mentioned using adaptive bit rate and moving different resolutions. Does it, I guess, close the loop and actually look at the adaptive bit rate stream and do things like chunk alignment and jumping from resolution to resolution? Is that measured in the index?
Yeah, so variation in quality is already considered in the index. That's one of the major factors with ODT streaming. One is, as I mentioned, rebuffering events, and we showed before. How long and variation and frequency and all of that in one way or another impact overall quality together with variation in quality. So the demo I was showing, it already is switching between different resolutions. So a uniform score, irrespective of whatever the resolution is, as long as you're able to maintain that and the score is accurate, then you can do it.
So you're turning the knobs on your codecs automatically.
Yeah, that's one.
So you have your source, you get a quality index of that, and I guess you have some sort of a tracking algorithm that looks at what you're doing to the video and turns the knobs on the codec to minimize the bit rate subject to your optimization loop.
So exactly. So that's the like I said, that's the first way of doing that. If you can re-encode your content.
Well, in order to, like your side by side, your A/B roll here that's showing the right hand side as being higher compressed, and that would be an example of what you're talking about. Right?
Yes. So, but the demo I showed is for smart video streaming, where you already have encoded assets at different bit rates, and we are switching between different quality levels, between different bit rates based on target quality. So what you would typically do is your target, whatever the highest bit rate you do. Right now, video is streamed based on best effort. So highest bit rate available, let's pick that. What we are saying is you don't need to do that. You only need to get the chunk that would give you your target quality. So it's a similar concept applied on streaming, but the same gains are achieved whether you do it the first way or the second way. Like what you said is exactly how you do it to optimize encoding. The second way I mentioned, the similar concept you apply when you stream it. So for example, if you know that you're streaming it on the phone and you can do 5 megabits per second, but the quality, you can achieve your target quality at 1 megabits per second, then you don't have to deliver 5 just because you can do that. But you need to have that understanding of quality experience to get this gain.
Thank you, everyone. I just get appreciation.
Oh, thank you.
And